Hey, hello, and welcome back to this Global Hack Week, Data Week. So, I know this is one of I think it's the last one, the one previous to last. Let me quick check. Okay, yeah. So we have this data composition in part three. Then we have me again, data pipelines that comes right next after this one. And then we have tomorrow Rosendo to give us an introduction to Google AI Studio. So I will recommend you to check that out. And then we have the closing ceremony. So I'm mentioning this because uh, I know it's low attendance at the moment, but I really hope you get a chance to watch this stream in a recording, right? This is part three. So previously on the first part, we check out the Kaggle platform. We even take a look to an existing notebook. We take a look to the entire platform, and remember, Kaggle is not only a platform; it's more about a community. So we give some examples about where you can find your data sets, competitions, notebooks, courses, a lot of things, but also a great community that can help you improve your data skills, right? So that was for part one. On part two, we check out the specific competition that was the Titanic one. We take a look to some experiments and we even make one new to improve our first submission. So we are increasing in the leaderboard, and the main intention for this part three is doing the same. We are going to start exploring some other alternatives. We are going to make some our data analysis, and we are going to even test some new models to see if we can make an improvement in our accuracy, right? Let me start sharing my screen. And well, yeah, please, I always forget to do this, but remember to register, sorry, to check in here at the link events.unleash.io slash events 12899, right? So you can win your community points. Amazing. So now let me do share my screen. Uh, okay, now sorry, give me a second. I will share the entire screen. Amazing. So you should see it right now. This is where we leave it. We were talking about the experiments, and also let me open the Kaggle submissions page. Let me see. Okay, here we have it, Kaggle, and we have the competition of Titanic. Again, we improve our leaderboard submission. Our latest was that. So we have a lower score, but the biggest score we have right now is this. Let's try to make it even better. The numbers of versions we have tried, or the entries. Okay, you see, for example, this is a lot of entries. Maybe he's trying to stay on the leaderboard for some time right now. Um, I don't know. It's a big gap, the one we have to cover, and a lot of them are under one closed, looking for teammates. Um, so this is a perfect score. And in the 150, we start getting some more real insights because I have to admit, this is weird. I don't know how they are doing this to get a perfect score. Maybe even we can try just Googling it because, again, this is an open. Um, an open competition. It's supposed to be for fun, for you to be introduced into the Kaggle platform. So right now we're just being ambitious, trying to increase our rating in the leaderboard. But why not? But I mean, I am not doing this over vanity. I want to learn how these other people are doing a better performance model that has an accuracy of 100%, which I think it's interesting. Don't you think? So let me return here. Remember, these are some of the examples we have run. We load the libraries. Okay, let's run them again. We load the data set. We inspect the data. We check also the test count because we have a train and a test set. Also, remember the problem we had on the overfitting of the random forest, which is for the experiment 6 um, random forest. We are not doing data splitting here, so let's try first doing the data splitting. So why not? Let's do that. Let's start with that. And for that, I'm opening scikit-learn, and I am going to look for the model selection and evaluation and supervised learning, dispatch, extend examples. No, I'll train split. Let's just look for a split. Train test split here. Train test split. Model selection. Okay, it's in model selection and evaluation. Training, metrics, and scoring. Cross validation and scoring. Okay, where's split? Okay, it's not weird. So we saw it was trying to split. So let's look at that. Okay, here it is. Trying to split from this is because I was not remember uh, where it was stored in scikit-learn model selection. Oh, we also have key fold. So let's also add then the train test split, comma, and just like that, we delete this one, we import a new one, and let's try to do one new. This is going to be for Markdown, and the experiment number 7. Try random forest with different parameters and train test split. And let me add the code for that. We are going to start doing the same. So select the columns, selecting columns, featured columns. Features. And okay, let's copy all of this and let's modify the things that we have. Also, I think that will be better thing to Yeah, you better use the random forest one. And this is not 7, this is 8. I forgot about that. Also, I'll be pending here on the comments, so if you have any question at any time, feel free to drop it here at the comment sections, right? Let's remember our data and how it was um, distributed. So you have data. We have survival, class, sex, age, siblings, parents, tickets, fare, cabin, and embarked. So let's add the embarked one because we didn't have it first. So survival, it's the one we are aiming to. So that's the Y train. Um, P class, sex, age, zip, links, parch, fare, ticket number. I don't think that helps. Cabin number, same. I don't think that helps. But let's do the embarked. And also numerical features. Again, this is age, fare, P class, sex, siblings, porch, and embarked as the categorical features. So for the numerical features, we were doing a scalar. Let's try without the scalar. So numerical features, right now we're not doing any of this. Let's remove the scalar. And for the one hard code encode for the categorical features, uh, let's also not do one hard encode for either P class or sex, just for the siblings. No, neither for these siblings, fair, embarked. No, we don't want this. Uh, so we're not doing that data processing, so we can delete that. We have the data frame of the manual select features. We make a copy for the train, we make a copy for the test, and from the train data frame, we take the white train. That's perfect. We convert sex fixture into numerical. That's also still a desired thing. And we fill the mean value for the age and the median value for the fare. Also, convert or encode embark feature. Same for test. That's great. And this is a misspell. Okay, yeah, I add another. And yeah, my bad. Let me take a look to the original data to see if the embarked, yeah, we're missing values on the embarked. So we have to treat them as well. Let's do that. So for this, we are going to fill embark values with the mount common port. Great. So you see, we are using the trim principle. Um, what's the word for this? In statistics, we have the mean, the median, and the mode, right? These three are really common. Remember, the mean, it's the average. It takes all the values out, it divided into the amount or the number of elements. The median, it's just taking about the position. So if you take a list of elements, you take the middle position, that's the median, and the mode, it's the value that repeats the most. So that's interesting, and it's a great approach because it does not tell us, like, for example, um, one value could be or the distribution here could be slightly charged to one way or another, and the mode will respect that and keep the distribution of the data. So that's why we're using that here. So we filled the missing values of the invert with the mode, and we also encode that to change the values from being S, C, or Q into numerical values, right? We're not using the min max, and we're not using the encoding for the categorical features. So then we are not using these um, scalars. Build the final train and test sets with the train encoded and the train scale. This is not a thing we want to do here. Then we create a model for the random forest. We have a big number of estimators, and now I'm also doing this, the max depth of 10 and the mean sample split in 5. Um, I'm not keeping the mean samples lift, but let's take a look also to the documentation here to see exactly what we're talking about, right? So if we go to the supervised learning and the compose or ensemble methods, here we can take a look to random forest, and in random forest we have the app, the class definition for that. We have a number of estimators, the number of trees in the forest, the default value for an estimate frame from 10 to 100. We are increasing that number to be 1,000. Um, Criterion, it's good to have Genie, doesn't matter. To do what they call is food support, Genie impurity and log loss, and entropy vote for Shannon information gain. Max depth, the maximum depth of the tree. If none, their nuts are expanded until all leaves are pure or until leaves contains less than a minimum sample split. Min sample split, it's the minimum of number of samples required to split an internal node. This should be an integer, so we're arcing that as 5. Let's see how it behaves. And well, that should be it for the things I want to change. And we train not with this, it will be X train without the final, and Y train. So here we evaluate the model. So the score for this, let's take a look to the, oh, my bad. Let's take a look to the score method to see what's happening. It returns the accuracy of the provided data and labels. So it's great. We're also doing this for the train and with the train values, sorry. And we see the score here, and then we visualize the results, right? Here again, we first make the predictions for all the train tests, and we compare it using cross validation with a confusion matrix for the Y train values. This confusion matrix for experiment 8, and this should be saved in a 8 value. Also, for the survived, it should be generated based on the test data. One thing we are missing, it's splitting our data, right? Um, First, we select the categories. So we have now the categories, and before training, we are going to make this split the data. split the data into training and validation sets. Train test split, this is going to be X train and Y train. The test size is going to be of the 20% of the original set, and I'm going to delete the random state because I want this to be fully random, right? So now we have an X train, and now we can call it final. X val, that's great how it is. Y train, final, and Y validation, right? So we changed how we train the model here for final and final of the X train and Y train. That's a great recommendation. Takes Copilot, and then we evaluate the model with the training data, and also for visualizing the results. And we also evaluate with the validation data. And that's with the values that we haven't seen in the past, right? So this is going to give us a better approach of how the real validation or how the real accuracy will be if we submit the answer to Kaggle. Because what happened to us before, it was that in the experiment 6 we had a really great score, but these were just for the training data, right? For the test data, we didn't make any split, so we are not sure how the model behaves based on new data, based on something that it hasn't seen. In this case, the validation sets uh, here. Let me look. Okay. Validation X and validation Y. This is data that the model haven't seen before. This was not part of the training sets. So this score, this accuracy, it's more likable to be the one that has the test result. So let's run this to see how it works. Wow, it's taking its time. So let's give it a time to for this to load. The random forest model score is 91. The random forest validation score is 86. So that's interesting. And the confusion matrix looks like this. So this it's good, but it's not the best. Let's try to submit this to see if or guessed it's close to this value. It should be close to this value, but let's try to run that again. And the values should change because the way we split the data is in a random way. That's why we delete the random seed. So let's just take a look to that again. Obviously, it's going to take that much time to train. And I wonder what happens if we increase, okay, around the same values, but still a great result, right? So let's try to make that submission. Okay, first, here and in the Titanic again, let's take a look to the submissions and let's submit a new prediction. This is for experiment 8. Let's submit and let's see what our new score is. Okay, it was better than previous, but still not better than the best one we have. So this first two, these 0.73, were with the random forest. This experiment 5, it's with linear support vector classification. This experiment 7, it's with support vector classification, but not linear, with GDR polynomials. And this experiment 8, it's again with random forest. We did make some changes. We increased the number of estimators. Let's see what happens if we increase them even more. And we delete the boundaries about the mean sample split and the max depth. Let's also try to see how many time it takes to load. And also let's visualize a little more our data. So try random forwards with different parameters and train the split. Also here we are doing more early data analysis and feature engineering. Being said that, I think the preview in some notebook, I saw someone marking something as the family size. So let's try to change the siblings and the parents to a family size feature. And for that, that should be, let's do it after the encode and before the split. Engineering for creating a new column of family size. Great. So in the in the data frame, we create now a family size that has the values of the number of siblings, the number of parents plus one, because that includes the the user in this case, or the row. And okay, that should be it. Let's try to run this as it is. So with that much elements, we didn't get a good validation score. So look, this is somehow what happened to us in the first stage. We have a really good score for training, but a terrible score for the validation, or the test one. So um, let's give it a little time, because I think it's still performing some operations. It's still running. Also, I'm going to reduce the number of estimators back again. Let's do 800. And let's return the limits of the max depth and the mean sample splits. What else we could do? Okay, one thing I am also thinking it's going to be interesting is for us to prepare the data. We can run some unsupervised learning or some clustering um, for making the reduction. But first, let's check the model selection and evaluation guideline. User guide, model. Choosing direct estimator resource, sorry. So for this, we want to reduce the dimensionality. We can pass this to a randomized PCA. If this doesn't work, we do have less than 10K samples, so the spectral embeddings or something like an ISA But I think randomized PCA, which is principal component analysis, will be interesting to see. For example, how the principal components analysis method works, it's that if we have some number of features, in this case, we have around one, two, three, four, five, and six, we can reduce it to be just uh, three or four features for the model to have a better understanding of what's happening here. Remember, not every time more information leads to better results. I mean, more data, it's a good thing to have, but you need more data to clean them a lot and get reduced number of parameters, right? Um, does this, okay, this is all still running. Let's try to run this with the new variable we created. Also, we reduce the number of estimators. Uh, this is a problem. Oh yeah, this is not finding the zip pin because this is not a next train. These ones are on train data frame, and this one's on test data frame. Great. Does that work now? Let's find out. Uh-huh. So let's keep exploring the principal component analysis. Exact PCA and probabilistic interpretation. PCA is used to decompose a multivariable dataset in a set of successive orthogonal components that explain a maximum amount of variance. In scikit-learn, PCA is implemented as a transformer object that learns in components, and in its fit method, PCA centers but not scale the input data. Mhm. PCA also provides a probabilistic interpretation. Uh-huh. Incremental PCA, principal components analysis, or ERIS dataset. Let's take a look to that to see a better example, and also open the PCA uh, method here. So how this works, let's take a look to an example. We use import PCA from the composition. We have an array, number of components we want to achieve. In this case, that's the n components, and components default known number of components to keep. If n components isn't set, all components are kept. Then that kind of that does not work. Uh-huh. So we fit the existing array of components. We print explained variance radio and the singularity values. Uh, the SPT solver examples fit the model with X array like sparse matrix or of shape. Training data where n sampled its number of samples and n features is the number of features. Uh-huh. Ignored. Fit transform, fit the model with X and apply dimensionality reduction on X. So, okay, seems like a good approach, but let's give a look. So, this gives us again good a good score here, but still it's 0.82, and we cannot achieve a 0.9 solution. This one it's even 0.85, which is interesting. Um, but changes. Let's see how this affects. Okay, without any restrictions, this value increases. It takes more time to train. Yeah. And the increasing could be just a stochastic result, not necessarily a better understanding of the data. Let's try to run it one more time. Yeah, still around 0.8, not not a better performance. Let's try the same about the reduction, but with another model. Um, mhm. Max feature, max leaf nodes, mean bootstrapped, OOB score, and jobs run state verbose, warm start, class weight, CC alpha. Okay. Mhm. Trying to understand default square the number of features to consider when looking for the best split. If int to consider max features of its split. Mhm. Interesting. Uh-huh. So this was the train split for Iris dataset. Okay, we can close this. For the example on Iris dataset, let's take a look to see how they did this. Plot of pairs of features for the Iris dataset. So, for example, here they reduced the Iris dataset to three components where it had four. So, unused but required import for doing 3D projections with matplotlib data. Okay. Uh, uh, uh. Yeah, so here the the keys are data target frame target names DSR feature names file name. Okay, so plot of pairs of features of the iris dataset, iris frame target, iris target names, iris dot target, iris dot target in target names, and these renamed classes using the iris target names. Okay, target Setosa, version color, virgin iris dot frame, and the hue it's based on the target. Each data point with the color. You can also plot PCA representation of this. PCA will create three new features that are a linear combination of the four original ones. In addition, this transformation maximizes the variance. With the transformations, we see that we can identify each species using the first feature. So let's try that. Let's try doing a reduction of this. So try running first with different parameters. Train data to split and PCA. Now let's once we have all of our features, let's apply PCA to reduce dimensionality. And I want to reduce it to three features, to three components. Um, Train PCA, it's going to be fit transfer for train final, for X validation, and test final. X validation, it's not already here, so let's first split it out and then apply that validation. Another thing, do we want to do? I'm not sure it, we should also. Okay, no. Just to the PCA model fit, model scored. Yeah, with the not with the final, but with the PCA, with the PCA here as well. Validation, PCA. Also with the trained PCA here, validation and test PCA. Amazing. Let's try this. X test file, it's not defined. Oh yeah, it's just X test, not the file. Okay, good. Let's run this and let's see how it behaves. If reducing the values for the no, it was awful. I mean, for the confusion matrix, like the this one for the training, I don't want to visualize the results uh, of validation in this case. Confusion matrix. Let's change all of this for the validation. And let's see. So validation comes from after splitting, and we split after we do all the engineering or the feature engineering to the data frame. So Yeah, it's too bad. I mean, like the training one, it's good, but this is just not good. Um, what happens if we apply the max depth and the as we were thinking and the mean sample split again? Still too bad. Okay, random forest had a better result without the PCA analysis. So let's delete this PCA and let's try to return to how this was before. Good. So we delete this, and I am going to create a new experiment. um, I'm going to paste this, and I'm going to copy almost everything here. Try PCH dimensionality and apply SBC, linear SBC. So after we did all of this, try and random forest, split the data. We split the data. Try linear SBC model, model fit. We delete all of this. We have the PCA. We update the SBC model score with model score and trained PCA. Also the Y trained final. Then we had the random forest, not the SB model scored with the validation. We changed the visualization of the results. This is for experiment 9. And this also is for experiment 9. This is for test PCA. And also this is for train visualize the results of validation. So let's remove that and check how it predicts. This time shouldn't take that much to load. Yeah, but the result is not that good actually. Uh, is this something that it's constant? Yeah, I mean it's lightning fast compared to the random forest, but it's not a solid approach. Actually, this is not good at all. Not even for the training data. So what we are facing here, at least, it's that, well, see, even here the validation, it's even better than the training. So at least here we don't have an overfitting or something like that. Uh, but this truly it's not good. So maybe now we need to apply more things. Let's try again to check how we are managing our data. So we have the class, sex, free class, give us Uh, train test, train. P class, it's the value or the number of the class of the ticket, name, sex, age, siblings, porch. Okay, maybe we can apply another scalar before we apply the PCA. Uh-huh. Random forest, no. Right now, another scalar. I need to clean my nose, so give me a little second. I'll be back. So we were applying before the min-max scalar. Let's take a look as well to the max absolute scalar and the Raman scalar to compare. And we also can compare the different scalars on data without outliers. So for example, in the comparison, we see, I think they have like a big chart here. Um, mm, 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 Gaussian output. What we're looking to have a Gaussian output or a quantile uniform output. Power transform road scalar. Unlike the previous scalars, the centering and scaling statistics of row scalar based on percentiles, then power transform or quantile transformer should be an interesting approach. Better normalizer, maybe a normalizer rescales the vector for each sample to have it norm independently of the distribution of the samples. Uh, huh. We were applying this before the min-max scalar, rescale the data such that all feature values are in the range of 0 and 1, as shown in the right panel below. However, this scaling compresses all inlines of the narrow range for the transform average house occupancy standard scalar. Uh, these are squeezed in a smaller one. Original data plot is this. Yeah, maybe doing something like the quantile or the normalized. Let's try first with the normalized. So normalizer. Let's go at the very top, and we have our scalars around here. Min max scalar, one hot scalar, normalizer. Great. So let's run this, and let's go back. So for example, let's let's first give it a try to plot like this uh, the data in the original and normalized one. So they do have a function for that here. Create access, plot distributions, dataset, xfull, yfull, feature names, feature mapping. Take only two features to make visualization easier. Feature Met Inc. has a long tail distribution. Feature average frequency has a few but very large outlier. So a lot of features scaled out between 0 and 1. Plasma does not exist in matplotlib. Create access. Define the access for the first flood. Bottom left. Scatter. Return. Flood distributions. Here, make the plot with the ETM index, distribution, what they see, average house occupancy and median income in block. House occupancy, median income in block. House occupancy, house average house occupancy in median income in block. So let's do something similar to that. We are going to plot um, for the P class. What will be good? The fare they pay for that. Hmm. I'm not sure. I'm not sure, but maybe we not need to focus about that. Maybe trying to reduce the components just with these. Before even we apply another scaling, let's change it instead of being SBC, sorry, linear SBC, just SBC. And for our previous version of this, what we were using, uh, 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 gamma, degree, and C. Let's copy this in. And let's see the output. Okay, no, this is way worst, but it's weird because for the test data it works pretty well, but for the validation one it's awful. Um, yeah, gamma here it's maybe too high. Let's try to change it just to 3. And degree, no, same problem. Okay, let's remove these and apply just base configuration. Now it's awful for all. So something we were doing was correct. Gamma of 2, degree of 5, and C of 1. It's it's too bad for the validation. Uh, why is that? Why is that? Maybe these are two elements. Let's change it to 5. Still the same happen. Now let's try to do the scaling then, and I'm going to apply normalization to, I'm going to apply normalization to age and no family size, and that that would be it. I think that will be it. Unfair. Yep, fair and family size. We use the normalized, extrain normalized transform. The same here. Seems great. So let's try to run this like this. Okay, it is better. So normalizing do help, but well, at least we have a constant better performance. Let's try to see how we can change because we have a lot of values in this corner, and I think it's interesting uh, to try to understand why we're predicting that a lot did not survive, but they do survive. Uh, let's try to return to the linear. Linear SBC. Okay, it got reduced, and we have five principal components. If we reduce the number of components, it's still not that good. If we did not reduce the number, I mean, if we keep without the principal component analysis, should that have a better approach? Let's try that. So for regular SBC of a gamma of around 8 with the same degree, I'm giving this an 8 value since we are having a reduced a big number of features. The principal comparing analysis then shouldn't be applied here. I mean, shouldn't be applied at all. So train PCA, it's just going to be train right now. Same here, same here, same here, same here, and same here. Let's see, let's see. No, I don't think or I don't feel this actually is affecting or it's changing. Even without that. Hmm, kind of fun because at least it's not marking that they survived, but they did not. So let's keep with PCA. Let's have a reduced gamma. I just want to reduce this to 5 and maybe a number of elements. Okay, no. Hmm. This is better. So let's try to upload the new prediction here to see the real output of it. Let's see if that actually make an improvement. Ugh, 77, but still not our best ambition this far. Linear SBC with the previous big amount of features was better. So we're still in the 0.77 row. Interesting. Linear super machine. 79. At least with linear, this distribution, it's not on balance. I mean, they do ask for the same number of um mistags in survived as in not survived. Uh, in the polynomial vector machine, this is not balanced. We almost have no survives and a lot of not survived mispredictions. I don't know why, I have to say. Um, let's keep exploring our data to see what we can change or what other feature we can extract. Um, what happens if we reduce the number of training parameters here at the random forest prediction? Being the validation set of dot 35 and the number of estimators, 1200. Same problem. It's not good. I mean, mm, confusion matrix. It's for the yeah, I want it for the validation. Yeah, yeah, that didn't make sense because it was a very good accuracy value for the test one. But what happened with the test data that's being overfitted here? Uh, and what happened if we reduce the number of estimates to the 100? Mm, mm, no, this not this is not the way. Support virtual machine. Let's take a look to our great guide in scikit-learn. K-neighbors could be, but for K-neighbors, we are not, well, any other ensemble, gradient boost trees, historic, histogram. Mhm, mhm. Random forest and auto randomized string symbols. Random forest classifier. Okay, I can close this and these scalars. We can try not with normalize uh, with the quantile transform to see if that helps. So support vector machine with the gamma scale on C1. No, this is not good. Auto. Well, it was better, but hmm. Let's see how that behaves now with the normalizer. Applies quantile transformation and quantile transformers should be at the beginning. Mhm. Mm, and quantiles. Oh, interesting. Yeah. Okay. For quantile transform, mm, okay. No, this is not good. But at least now it's not on balance. Well, no, yeah, it is too on balance. No, 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 no. Okay, okay. Apply, normalize. Normalized. And this is to fair age family size. No, let's do the mean max scalar. This degree. What's the maximum value for degree. Oh my god. Degree, it's normally 3. Yeah, it's default 3. I'm going to use kernel RBF. Huh. Huh. No, it's still big misinterpretation here. Let's see for the fit time scaled at least with the number of samples maybe. Uh-huh. Okay, yeah. Um, wow. A lot of misinterpretation here. Uh, uh, now the problem this is learning, but it's not being applied to the result. Hmm, took a lot and the result is awful. Same as this. Although I think it performed better. Oh my god, no. Mhm. Okay, well, this was an interesting experiment, but I think we need to continue. Um, we haven't managed, and even if we did different transformations to our data, previously we were doing one hot encoding that added a lot of features. Right now we are not. Well, that's another thing. We're not considering. Um, okay, let's try that as well and apply SBC, maybe even linear. linear, linear. Uh, so linear is not that bad. And one thing we could do, let's return to this. And yeah, we're not considering here from the original data. Uh, um, Siblings and parents independently, right? So I don't know. Maybe it was some magic in there. Our best result is this. This is our best result. The experiment five, considering the class, the sex, age, sibling, parents, fair, and applying min-max scalar to the numerical features, uh, age and fair, and for the categorical as P class, sex, siblings, and parents, we are applying some one hot encoding. So for sex, that's weird. I don't want to apply being a categorical feature. So sorry, on one hot encoding. For siblings, parents, we did change this to be just family sized. For categorical features, we had tried, and also having all of these takes out all of the intention of having a PCA, right? Um, if we return the number of elements to not reduce anything, our approach is kind of the same. I don't see these effects at all. So, so we have our one, two, three, four, five components with the variance radio. Uh, okay, yeah, let's delete the PCI. Data processing, just like that. And let's reduce. What? Are we applying min-max scaling? No, let's return to the normalization, norm L12. Uh, let's delete the PCA. And let's see. Okay. Why is this? Because this is linear SBC model, just SBC. Okay, well, um, before we run out of time, I want to see if we can find any in that book, any hints on how to tackle this. So we have the Titanic tutorial. We already checked this, uh, and this suggests to use random forest. This other tutorial, this is for TensorFlow. Decision forest should be really similar. TensorFlow, TDF, load data sets, prepare the data set, what processing this gives, normalize the name, and apply ticket number, ticket item. So it has name, sex, fare, embarked, a ticket number, a ticket item, uh, uh, input features, convert pandas dataset to train the model with default parameters, accuracy, you see, gradient boosted trees model, uh, train the model with improved default parameters. Now use some specific parameters when creating the GPT model. Uh-huh. And the accuracy is worst. uh, Make predictions. Hyperparameter tuning, making an ensemble. This is but what's the output for that? For well, what are else? Titanic dataset original, MLR3, decision tree, task, my first project, Titanic competition trial, Titanic month prediction. Let's sort them based on hotness. Oh, uh, I still have another session. Remember that the pipeline is coming up. I'm going to give it a 15 minutes boost. So this is the time we have to end this session, and then we are going to make a pause to the next session. But this was the last session for this series, right? If you want to get more detailed information of what we're doing here, because here we're making a lot of assumptions that you already know what I'm talking about for these data treatments, and we're only focusing on the solution. Again, you want to understand more in basic terms what's happening here. The next session, it's perfect for you. So based on hotness, based on most votes, Titanic data science solutions, introduction to assembling and stacking with Python, the science framework to achieve 99% accuracy. Heh. Let's take a look at this. Uh, Also, well, this was 8 years ago, an interactive data science tutorial 9 years ago. Let's see. Mm, Classifying, correlating, converting, refactor released. So same. It's using logistic regression, linear SBC, support vector classification, same as us. Uh, Random forest classifier. We didn't use the k-neighbors classifier, Gaussian NB, perceptron, so perceptrons. Stochastic right in the center classifier and decision tree classifier. So we first acquire the data. We have these existing columns. So we identify categorical and numericals. Yep. Yes. The difference between continuous and discrete. That's great. So which feature contain blank? Well, we already did this. What's the distribution of the numerical values across the sample? Okay, yeah, we already take a look to these descriptions. Assumptions based on that analysis, correlating, completing, correcting, creating, classifying. Let's take a look to what he's doing. So it's grouping being the P class. So a lot of first class survived more than the third class. Same here. We see more female sex survive than males. And for the number of siblings, uh, if you have more siblings, it's a lower chance to survive. Same with the number of parents. So we realize smaller groups of family had more chance, except for three. I don't know what. Why is that? So observations: infants, high survival rate, oldest passengers survived, large number did not survive. See, yes, decisions correlating. Mhm. Wrangle data, model, predict, and solve. Creating new features, extracting from existence. The title, I see a lot of people did this. Like if someone had a title, for example, these Captain, Cole, Collins, Dunn, John, Lady, Major, Master, Miss, Smile, a lot of things like that. Um, and we convert that into categories. So it has the passenger ID, survived, class name, sex, age, spiel, field, mark, title, converting a categorical feature. So survived, P class, sex, age, siblings, parts, fair, embarked, and title. Completing a numerical continuous feature. Uh, Creating new features, combining features. We already did this. Family size. We create a family size. Hmm, the magic number is four for surviving. We can create another feature called is alone. If it's zero or one, that has drop parents, siblings, and families files features in favor of it's alone. So no any group not using the family size, but the factor of if it is alone. Same, we're still having the embarked. We can also create an artificial feature combining class and uh, age and class. I don't know why this is for categorical, contributing categorical feature, converting categorical to numeric. Of course, we did that as well. Completing and converting a numeric feature. Well, we did all of this. Then I'm guessing why we don't have a greater um, result. Train, logistic regression, the output's not bad. Super vector machine, features. Okay, yeah, we kind of have these on training, but not on test. King neighbors, Gaussian naive bias, we do same as this. We didn't use perceptron, linear SBC. We did better even with linear SBC. Um, SGT classifier. Oh yeah, we didn't use bias, but yeah, we did use stochastic gradient descendant classifier, and it was not that good. Same with decision tree, it was not this good. It had a number fit decision tree. Well, not we used random forest classifier. Um, it's weird. So random forest got a better score, but these were for the training data. Even we have a better performance in this, but not for the test data. So we do have a number of it problem that we could not correct, or we were able. It's interesting. And the interesting thing is that we did all of this. Here, for example, this assures you it's going to give you 99% accuracy. So let's take a look to that. Gather data, prepare data for consumption. Come on, load. Don't know why it's not loading. But let's see also. Uh, most comments, hotness. Hmm. Recently run, public score. How top leaderboards for their score. Top solution. Okay, let's see. This notebook, it's about Titanic, okay? Public score, it's 100. What? I will show you how it's easy to get a perfect score on the LB. All you need to do is download the test data with the ground truth labels from here, add it to your private dataset, and make it public from the notebook, and you will see yourself in the top. Yeah, this is what I was mentioning. For me, it's completely weird to run a LM model and have a perfect score. I think people do this just for being in the leaderboards. um, I don't know why they do that. Yeah, don't do this, people. Well, if you want to be on the leaderboard, it's okay. But there's no reason for doing that. We're using this for educational purposes. I think he understands this. Try to not cheat in this notebook. It's only for educational purposes. Yeah, for sure. In this kernel, I will show you how it's easy to get a perfect LB. All you need is not only that, test data with the ground truth labels from here, and I did okay. Uh, then run the column and see yourself in the top 0.5%. The point, cheating can never get you anywhere in the long run of your future. Yeah, yeah. Okay. Well, 99% accuracy. This shouldn't be cheating, I think. Um, gather data, prepare the data for consumption. Libraries, load model libraries, deforce if data clean, convert formats. So it's using a feature that is alone. Uh, one hot for sex, one hot for embarked. Double check the clean data. Okay. split training data. We also did that. Perform exploratory analysis, uh, model data. Uh, uh, Evaluate model performance. So this is comparing a lot of methods as well: Gaussian ensemble methods, naive bias, super vector trees, super vector machines trees, and discriminant. And also XGBoost, which again I don't know what is it, and what's the output of it. They go up to 0.89, yeah, like for decision trees, for example. Random forest here, train a test. This is the one that's interesting. We didn't manage to get these high results. Even with the supervector machine, we only got these on our test. What's for the accuracy tree SDT? But for our validation sets, we do get these ones, but for the real test data, we don't get that. We just manage these 0.75. But hey, I think we're under the terms. I mean, our leaderboard was not that bad. So, yeah, I feel happy with this. We even create some more experiments. And in difference to these first 115 elements, ours, it's really um, the data processing and data analysis what led us here. So, well, I think I'm happy with the result. I hope you enjoyed the process and trying to solve this with me. I really appreciate you were here, and I think we can close this for good. And well, for all the experiments made here, I'm going to share them with you. Um, Let me add the modification. Okay, it's now under the repo I previously shared. If you don't remember the repo, let me share it with you. Yeah, we need to go to the data pipelines. This was Titanic. Well, let me look for the repo, don't worry. Okay, yeah, the Titanic cable competition. This is the repo. So it already has the change made in live session. And let me copy and paste it here for you on the comment section. Thank you so much for joining me in this trying to improve our Kegel submission here. We do get some interesting experiments. Unfortunately, we didn't manage to get our higher rank in the leaderboard, but we are sure that now the perfect solution does not exist. That is just cheating, and well, I think we did some interesting insights on data. We apply really interesting also machine learning models, classical models. Of course, we could use some of the heavy weapons in the future to try to get better results or better predictions. Yeah, I'm talking about artificial neural networks. And if you do want to get more in touch with data, remember, Kaggle is not just a platform, but it's a community. So go and join Kaggle Discord, right? Thank you so much for joining. Remember, we still have more sessions coming up for you. One of them being the next, which is data pipelines, where I'm going to talk like in a more beginner way uh, for the ones that don't know what I was talking about during this session, what an early data analysis is, what an ETL pipeline is, how it relates to a pipeline, what's a pipeline, how to process data, what's a scalar, uh, I don't know, things like that, right? So if you're curious about it, join me in the next session starting in 10 minutes. And also, don't forget to join the closing ceremony for Global Hack Week. And before I forgot, please, please, please share your feedback in this link. And well, that was it. Thank you so much, and I will see you.